Hi, today we are going to be covering about basic principles of microwave heating. We will begin by understanding three modes of heat transfer, which is also true even for non-microwave heating. That's conduction, convection and radiation. Conduction is a mode of heat transfer where the heat is transferred from one part of a hot body to another part through conduction between the particle or the molecules. Convection at the same place is heat transfer by way of convective currents that are set up in a fluid. And radiation is a mode of heat transfer that takes place without any medium being present between the hot body and the surrounding. The conduction heat transfer and the convection heat transfer both in a way primarily depend on three factors. One, what is the temperature difference between the source of the heat and where the heat is going to be transferred. The second factor is the area of heat transfer. And the third, there is a coefficient of heat transfer for both conduction and for convection. As compared to these two methods, radiation plays slightly differently because in radiation heat transfer, there is a factor of 4, or I would say temperature raised to 4, which governs the heat transfer. Meaning, if the delta T between the source and the surrounding is X, that is, as you can see from the formulae, it also depends on the coefficient of heat transfer. There is a constant which is called as Stephen's constant, and also there is this power of 4 of the temperature of the source body. These three being modes of transfer is true in case of any heating process. Once an object starts getting heated in a microwave system, these three methods or modes of transfer come into play. With this, let's go to the basic principles that govern microwave heating. Microwaves, as we have understood, are electromagnetic waves which are contained in a cavity and are radiated onto the object which I want to heat. The objects primarily are dielectric materials, and hence the microwaves flow through these materials, or rather I would say they penetrate through these materials to generate heat in the object. The fundamental equation which governs the microwave heat generation is 2 pi f epsilon naught epsilon r EI square, which shows that there are three factors which decide the amount of heat generated in the material. Two of them are properties that depend on the incident waves, and one of them is a parameter that depends on the material itself. Frequency and EI, which are the properties dependent on the incident wave, are primarily decided based on the generator which generates these microwaves. The epsilon r, which is the loss factor that decides the lossiness of the material, is a material dependent characteristics. Amongst the two properties or two parameters that come off the incident wave, frequency is something that is not a variable in a given system. A system is designed to generate microwaves at a particular frequency, and we do not vary that usually. So the only factor that is available for a system for the temperature control is the electric intensity of the incident waves, which means at a given frequency, if I vary the electric intensity of the incident wave, then the amount of heat generated varies. More the intensity, more is the amount of heat generated. Similarly, if for the same frequency and for the same electric intensity of the electromagnetic wave, if the lossiness of the material is more, that is the epsilon double dash is more, the heat generated in the material is more, and if it's less, the heat generated is less. Now, another factor, another term that is used very commonly in microwave heating is called as penetration depth. What do we mean by penetration depth? It is the depth of the material at which the incident electromagnetic wave intensity reduces by a factor of 1 upon E, which when converted into percentage, it is distance at which the incident wave intensity reduces to 37% of what it was at the surface. So if I give X amount of energy, or there is X intensity of energy at the surface of a material, at a particular distance through the material, inside the material, the intensity reduces to 37% of this incident value. This thickness or this distance is called as penetration depth. Depending on again the lossiness of the material, this depth changes from material to material. Penetration depth is again a function of two parameters. One, the wavelength of the incident waves, and two, it is the lossiness or the loss factor epsilon double dash of the material. The relative permittivity, rather I would say the dielectric property or dielectric loss of the material is the another factor. Both these factors decide at what depth my intensity reduces to 1 upon E or 37%. It is also important to understand that it takes approximately about 5 penetration depths to make the intensity of incident wave to almost zero. Meaning, at a depth of the material from the surface, which is 5 times the penetration depth, the intensity of the incident wave reduces to less than 1% of what it is at the surface, and which for all practical purposes is assumed that the intensity is absorbed in the thickness of 5 penetration depths. For particular materials, let's take an example of water. For example, water at room temperature, the penetration depth is very small, between about 2 to 4 centimeters, meaning 37% of the intensity is reached just at a thickness of about 2 centimeters when the water is at room temperature. But the same water, when it is heated to 70 to 80 degrees Celsius, the penetration depth increases, meaning the intensity of electric field or the electromagnetic wave is not reduced, and the heat conversion is poorer as the temperature raises closer to the melting temperature or boiling temperature of the water. In the other side, if the water is in the form of ice, something very interesting phenomena happens. That is, in the form of ice, the water penetration depth is very high, which means the waves that penetrate into the ice are not absorbed and not converted into heat. Rather, the waves travel through the ice for a very long distance without getting attenuated to a smaller value. That is why it's very difficult to heat ice in a microwave oven, whereas very easy to heat water. So as I said, the penetration depth for different materials is different. Depending on the penetration depth, we use certain materials as absorbers, even sometimes as a primary absorber. Supposing if I want to heat a substance with microwave heating and the material is not a microwave absorber, in that case we use a primary absorber around the material, and the primary absorber absorbs the microwaves, generates heat, and in turn it can radiate the heat to my object which I want to heat. This is in a way indirect heating, but also a very common system configuration that is observed in microwave heating. Another term that we very oftenly hear about in microwave heating is called the loss factor of a material. Loss factor of a material meaning it's how much lossy is the material, how much of the incident microwave energy it converts into heat. If a given material like Teflon or quartz, if you assume for example, the loss tangent or the loss factor is very low, which means the amount of energy stored in it per cycle of the incident wave is much larger as compared to the amount of energy that is lost, because tan delta, which is the loss tangent it is called, it is defined as the amount of energy lost per cycle divided by the amount of energy that is stored per cycle. So if the lost energy is higher, the loss tangent is higher, and these are the materials which are ideally suitable for using in microwave heating, or rather these are materials which can be heated with microwave very efficiently. And the last term that I want to explain in this series of lectures is about skin depth. Skin depth is the depth of material. This is primarily used in transmission of microwaves, not so much in heating a process. But supposing if I am transferring microwaves from one point to point B using a conductor, and these microwaves are traveling through the conductor, there is an EMF induced in the conductor and there is a opposite current that is flowing, which nullifies the current at the depth of the conductor, because of which the current flowing, the effective current flowing in a given conductor is limited to a certain thickness of the conductor from the surface. This thickness is a function of frequency in an inverse manner. Higher the frequency, the thickness is lower. And at microwave frequencies, this thickness is so small that the entire current tends to flow only through the surface. In fact, most of the current is nullified, and the current that I am expecting to flow from point A to point B is marginal. That is why using conductors for transferring energy at microwave frequencies is a very challenging task. A very special conductors need to be designed to be able to transfer energy from point A to point B. That's why I use things like waveguides, which will be my subject for another session. But coming back to these basic principles of microwave heating, there is a very common notion which we hear when we are talking about microwave heating. I've heard it from many people who say that traditional methods of heating are outside in heating, meaning I heat the outside of a material first, and because of conduction or convection, the heat enters into the deeper parts of the material. Whereas microwave heating is inside out heating, which means the inside of the material is heated first and then the heat goes from inside to outside. I would like to correct it because that's not a right way to look at microwave heating. Now that you understand what is penetration depth and what happens when microwave is incident on a material, at every layer of the material thickness, the microwave energy is absorbed and its intensity is dropping. So technically speaking, the intensity available for heating in a given material is any time higher at a surface as compared to a point inside the material. So it cannot be possible that the core is heated more than the surface, because we also analyze that the amount of heat generated in a material is directly proportional to the square of the intensity. So higher the intensity, higher is the heat. Supposing the dielectric property of my material is uniform and the frequency that I am using is also fixed, so the only parameter that is different at the surface and inside the material is the electric intensity. The intensity is higher at the surface and lower at the core. So naturally the heating has to be lower at the core and higher at the surface. But why is this notion come up that microwave is inside out heating? That's primarily because if you have a shell and if you keep a substance at the center and microwaves are incident on the material, no doubt the surface heats more than the core, but very soon the phenomena takes over, the phenomena of radiation takes over. And because the entire ambient around the material is not heated, only the object is heated. So what happens is the object becomes the source of heat and the environment is at lower temperature and the heat starts flowing from the material to the environment. Due to this, there is a heat flow setup and this heat is flowing very easily from the surface. So even the core of the material which is getting heated is now trying to give out heat to the surface because the surface temperature is dropping because of radiation. So very soon the entire dynamics changes in such a way that the core of the material rises to a temperature which is much higher. This is how the notion is different in terms of inside out heating. It's just a notion where it is in steady state we achieve this and not at the initial condition. So with this I would like to conclude the microwave principles or the basic principles of microwave heating. I hope you understood how the microwave heating takes place, what factors decide the phenomena of heating. Thank you.